Welcome to the kinematics of rigid body motion. Today we are going to discuss formal properties of the transformation matrix. So we know so far that we can write the let's say primed coordinates of a vector as a linear combination of the laboratory coordinates, combination given by an orthogonal transformation. And we know that we can go a step further and write, let's say, the components of the vector in a double primed frame as a linear transformation of the primed coordinates. So from these two, it follows that the double primed coordinates can be written in terms of the laboratory coordinates through the compound transformation here, which is found simply by replacing the primed coordinates here by their expressions. But we should also be able to obtain the double primed coordinates through a single transformation of the laboratory coordinates. And then it follows that the matrix elements of this single transformation need to be given by the expression here. And you can check immediately that if you if you take the sum of these products of the elements of the matrix C, then you immediately contract these sums into a Kronecker delta, which follows from the fact that the transformations A and B themselves are orthogonal. So the conclusion is that the product of two orthogonal matrices is also an orthogonal matrix, which is a specific example of what is known in mathematics as a closure under the group property. So we have found that the matrix C is given by the product of the matrices A and B, but we need to take note of the fact that the product, let's say B times A, is usually different from the product A times B, where these are obviously matrices, because for example, the matrix D given by the product of B and A we'll have the expression here, which is generally different from these ones, because we are summing over different combinations of elements. So therefore, matrix multiplication is generally non-commutative. However, it is associative. And this can be proven very simply if you look at an arbitrary element of the difference between the product of matrices given here. So A times B then multiplied with C minus B multiplied with C and then multiplied with A, you will see that you immediately obtain identical expressions for both terms, so they cancel out, and as such, matrix multiplication is associative. Now, vectors can be written as column matrices as well. So in this way, either in the laboratory or in the primed frame. And then if we apply the matrix A to the matrix of transformation A to the column matrix X for a vector and look, let's say, at component I, it will be given by the linear combination here, which is just the primed component. So the previous result for 419 is entirely equivalent with this matrix representation of the transformation and the vectors themselves. The addition of matrices is given by the definition here. There's nothing unusual about it. We have used it already. But more important for further discussion is the idea of the inverse of a matrix A, which is denoted by the expression, by the symbols here. And in order to find the inverse of a matrix, and to find the relations that are characteristic for it, we need to realize that transforming from the primed coordinates to the laboratory ones, or the other way around, it needs to remain consistent. So for example, if we take the transformation here and plug it into the second one, we we obtain the equation here. So from here it follows, since the components on the left and right hand side need to be the same, it follows that these matrix elements need to obey this kind of orthogonality condition. So and this one holds because all the components of the vector written in the prime frame are independent. So if we write the unit matrix in 3 dimensions by the definition here, then we can write this condition in matrix form as saying that the inverse of a matrix A satisfies this equality. So the product between a matrix and its inverse needs to give the unit matrix. And then with the unit matrix itself, we can define the identity transformation as given here. So a vector is equal with the application of the identity matrix to it, and multiplying an arbitrary matrix A with the identity matrix is commutative, as we always obtain the matrix A. We can also solve the two sets of equations the other way around. So we can plug the second one in the first one, and what we obtain immediately is the contraction here. So in this particular case, the matrix multiplication is commutative to once again reduce to the identity matrix. Furthermore, if we look at the product of 3 matrices and use the fact that matrix multiplication is associative, we can, for example, contract on the sum of the first 2 elements to obtain the result here, or we can contract on the last 2 elements to obtain the result here, but these two need to be equal. So what we have obtained in effect is that the inverse is identical to the transpose for orthogonal matrices. And furthermore, if we put results 433 and 435 together, we obtain the orthogonality condition in this form. And once again, we can show immediately by doing a simple multiplication to the left and right with the matrix A and its inverse, that in this particular case, matrix multiplication will be commutative. Now, if matrix A is of a dimension having m rows and n columns, its transpose is going to have n rows and m columns. And then if X is a column matrix, so its dimension is going to be given by m rows and 1 column, and its transpose will have 1 row and m columns. And then the product between matrices A and B makes sense only if the number of columns in A is equal to the number of rows in B, as implied by the definition here. Now, if we apply the matrix A to a column matrix X, this is entirely equivalent to, so this is an application from left to right. This is entirely equivalent to a reverse application going from right to left of the transpose of A on the row matrix X. So this equality holds. Now, if a given matrix A is has its elements identical with the transposed ones, we say that this matrix is symmetric. Whereas if the elements are equal only up to the sign, we say that the matrix is antisymmetric. And you see immediately that in order for anti-symmetry to hold, the necessary conclusion is that each diagonal element of the matrix has to be equal with 0. Furthermore, if we define a vector G as being the application of the matrix A on a vector F, and then we transform G as well for the matrix B, then using uh, the properties of the inverse of a matrix, we can write the application of B on G as being the application of B on F multiplied with a new matrix A prime given by the product here. So B applied to A applied to the inverse of B, and this kind of product of matrices is known as a similarity transformation, and it has several useful properties. For example, if A is antisymmetric and B is an orthogonal transformation, then if we perform a similarity transformation on A through B, it follows immediately through a very simple proof that that antisymmetry is preserved under a similarity transformation. Furthermore, for an arbitrary matrix A, the trace is defined as the sum of its diagonal elements. And then, if we once again perform a similarity transformation on A through the orthogonal matrix B, we see immediately that the trace is the same. So the trace remains invariant to similarity transformations. More generally, the adjoint of a matrix is defined as the complex conjugate of the transpose of that matrix, and a generalization of the orthogonality condition is called the unitarity condition, which says that the product of A with its adjoint is commutative and reduces to the identity matrix. If the matrix A is equal to its adjoint, we say that the matrix is self-adjoint or Hermitian. And a couple of things that can be shown immediately are that if the matrix C is given by the product between the matrices A and B, then its transpose is equal with the product of the transposes of the matrices in the reverse order. So the transpose of a product of matrices is given by the reversed order product of their transposes. And similarly, if we look at the adjoint of matrix C, then we can show that the adjoint of a product of matrices in just the same way is equal to the reverse ordered product of their adjoints. And for a matrix B, which is diagonal, having dimension n times n, and with the matrix A defined as its exponential through the power series expansion of the exponential here, the following identities hold. We will not prove them here, but they're very easy to see by applying this the definition of the exponential of a matrix as given here. All of them follow quite naturally, and this kind of representation is useful when working in a slightly more abstract context, namely with the matrices B being the elements of a Lie algebra, And this kind of representation of the exponential of the matrices will define the elements of an associated Lie group, which are the matrices A, and this is something that we will return to at various points in these discussions. The determinant of a square matrix is denoted by the symbol here, and it one property that is important is that the determinant of a product of matrices is equal with the product of their determinants, and as such, if B is a square matrix of dimension n times n, the determinant of minus B is immediately given by the result here. So it's minus 1 to the power of n, where n is the dimension of the matrix times its determinant. From the property here and the result 436, so essentially taking the determinant of the unitarity condition, we find that the square of an orthogonal matrix's determinant is equal to 1. So for orthogonal transformations, the determinant is always plus or minus 1, and this will be a very important point in the discussion of the kinematics of rigid bodies. Furthermore, assuming that A undergoes a similarity transformation, this is equivalent with the expression here, and if we take its determinant with the result here, and now since B is the determinant of B is non-vanishing, given that B has an inverse, we can simplify and prove that the determinant is also invariant to a similarity transformation. So in summary, we have reviewed various formal properties of the transformation matrix, including, among others, the product and addition of matrices, as well as the idea of the inverse, the transpose, and the adjoint of a matrix. We have stated the orthogonality condition in the language of matrices and related unitarity condition, together with the concept of similarity transformations. We have investigated the values of the determinant of a square orthogonal matrix, as well as its properties under a similarity transformation. And we will use all of these properties and others in the ensuing discussions. And in the following, we will investigate the Euler angles. So, with that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.